What's good, my statisticians? This is Professor Sampson from PS I Love Math, back with another statistical banger. Today we're going to continue our series on probability. I'm going to introduce you to independent and dependent events, along with conditional probability. And just when you think you had enough math, I'm going to hit you with the fundamental theorem of counting. So sit back, grab your pencil, calculator, and maybe even a drink. And don't forget to like, comment, and subscribe. I'm out of here. Period. Today, as I said, we're going to be covering 4.3, which are the multiplication rules for probability. Now, this section is not as easy as the addition rule. If you want to check the addition rule video, you can click on the link at the end of the video. So the multiplication rule is a little bit different because in the addition rule, we talked about a single event, like rolling a die. Only one event was occurring. That's the addition rule. Now we're going to talk about more than one event occurring, like a second event occurring. So you do something and then you do something else. So that is going to be a two-step process, which we call a multi-stage experiment. So with the multi-stage experiment, we're going to work on how do you do that for independent events or for dependent events, depending on whether you're going with or without replacement.
I have no idea what you're talking about.
All right, so let's get started. The first thing we want to talk about, as I said before, is a multi-stage event. So let's do some definition. The first definition we're going to talk about is a multi-stage event. A multi-stage event is an experience with more than one step. The second definition we're going to go with is independent. And if you recall, we defined independent before. When we talk about an independent event, we talk about whether one event occurring affects the probability of the other event occurring. So we want to talk about these independent events, okay? Independent events are these multi-stage events that we do that are with replacement. So what does that actually mean? That means that, let's say I have 10 things. I pull out one and I put it back in. That's with replacement. I have actually replaced my whatever that thing was. So if I had 10 different marbles, I took one out and I put it back in. That's with replacement. And with replacement is independent event. That means nothing's affected. So if you take out one card and you put it back in, or you take out one marble and you put it back in, your next choice is not affected. So if I have 10 marbles and I take out one and I put it back in, for my next choice, I still have 10 marbles. So I haven't affected anything because it was with replacement. So it's independent, meaning that they do not affect each other. So remember, these are multi-step events in multiplication. So you'll have, let's say, 2 events. So if you have 2 events, your question is, does the first one affect the second choice? And if it's with replacement, it cannot affect the second choice. Let me repeat that. If it's with replacement, it cannot affect the second choice because you have taken it out and put it back in, so that the second choice still has the same probability of being chosen as the first one. Again, if I have 10 marbles and I pull one out, so I have 1 out of 10. When I put it back in to make my second choice, I still have 10 marbles. So my probability again is 1 out of 10. So that's independent when we do with replacement because the second choice is not affected by the first choice. And when we have independent choices, we're going to move to our first multiplication rule for probability, which is going to be the multiplication rule for probability of independent events. So we're going to talk about the multiplication rule of probability for independent events. And what does that mean? That says that the probability of an event, of event E and F, is equal to the probability of E times the probability of F. Multiplication rule is the AND rule. AND means multiply. And if we recall from our last one, OR means add. So AND means multiply. So we're looking for the probability of E and the probability of F. We're going to multiply those two probabilities together. And that is the multiplication rule for probability of independent events. Remember, events that do not affect each other as you go from one event to the next event. I'm going to repeat a lot of things because students get confused with these different things. Remember, OR is addition and is multiplication. Independent means that the probability of your second step, this is multi-step. Remember, multiplication talks about multi-step when addition talks about a single step. So the probability of one event does not affect the probability of the next event in your multiplication rule when we're talking about independent events. Whew, what was that? Ooh, I already need a matcha. So what I'm going to do different about this section is this section has a lot of meat in it. So instead of waiting to the end to do all of the examples, I'm going to do an example after each stage so you can see what we're talking about, okay? Let's try the example for this. So we're talking about the multiplication rule with independent events. Okay, here's our example. So cut it off a little bit, but carriage rides in Charleston, South Carolina are unpredictable. You never know beforehand what part of the city you will see on your tour. Horse-drawn carriages pull up to a check-in gate at the start of the tour where they are randomly assigned one of the city's 4 routes. A monitor chooses a ball with the number on it, assigning your carriage a route. What is the probability that 3 carriages in a row receive the same route assignment if the balls are replaced after each assignment? So this is an example of with replacement. So that's a lot of reading. I know a lot of you are going to get caught up on a reading, but just go to the end. Like I said, what is the probability, right? The probability that 3 carriages in a row receive the same route. So you choose carriage 1 and carriage 2 and carriage 3. What's the probability of getting route 1? So let's look at that. 1 out of 4 route. That's your probability of getting the route, a route 1. So if you put it back in, the next route still has a chance. The next person comes up and 1 and 2. They still have a chance, 1 chance out of 4 at getting that same route. And the same thing for the third one. They have a 1 out of 4 chance, since you put the ball back, of getting that route again. So 1/4 times 1/4 times 1/4 is actually 1/64. However, I'm going to pull it up on my calculator. I'm going to have 1/4, 1/4, using your parentheses, right? 1/4 times 1/4, because you're doing the first one and the second one and the third one. So you have 0.0156. 0.0156 is your answer. Or if you hit math and enter, but I don't suggest necessarily that you do it because you already have an answer. It's 1/64, right? So 0.0156. So this is an example of when the probabilities are independent and one does not matter because you're replacing something. So hopefully you understand that example. So with that example, let's move on to where we're going. So with this, we had with replacement. This was with replacement, right? The balls were replaced after each one. This is with replacement. So let's move on. Let's talk about without replacement. What do we do when it's without replacement? Well, how does that work? Then these events would be what? They would be dependent. When we use without replacement, that means that the first choice is going to affect your second choice. So that is when you don't replace it back in. Your first choice is going to affect your second choice. So that means that these two things are dependent as opposed to independent. So let's get in the definition of dependent event. 2 events are dependent if one event happening influences the probability of the other event happening. And this is the event that we say is without replacement. So the first one was with replacement, and this one is without replacement. That means that you're not going to put it back. So that's going to affect your next choice. For example, again, if you have those 10 marbles and you take 1 marble out, that's 1 out of 10, all right? Now, if you put the marble back in, the next choice is 1 out of 10. But if you take the marble out and put it in your pocket, that was 1. If you take the marble out and put it in your pocket, the first one was 1 out of 10. But now when you go to take the second one, you're going to choose 1 or whatever that number is out of what? Out of 9, because you no longer have the same number of possibility as you had at the beginning. Hopefully that makes sense. You don't have the same number of possibilities that you had before. So we call this actually conditional probability, because that means that your condition is based on what you did the first time. Conditional probability, okay? And conditional probability, another definition, conditional probability, and we call that the probability of F. And this line here is given that. The probability of F given that E has already occurred. That's what that means. That means the probability of F given that E has already occurred. So that's how that is read. The probability of F given that E has already occurred. So something has already happened. So now you have a different set of probability. And we'll call this new rule the multiplication rule for probability of dependent samples. Okay, so the first one we had was the multiplication rule for the probability of independent samples. This one we're going to call the multiplication rule for probability of dependent event. And that just means still the probability of E and F. Why? Because it's multiplication, right? So that's going to be the probability of E and F is the probability of your first event, right? The probability of the first event times the probability of your second event, given that your first event has already occurred. The probability of your second event, given that your first event has already occurred. So if it affects your second event, then you need to know that that's going to be conditional probability, or that's going to be an event that's going to bother your prior event. So you know that that's going to be a dependent event because your answer is based on after you do the first event, then your second event will depend on what happened in the first event. This is getting deep. I definitely need a matcha. Here is our example for this one. Now, again, it's reading. Yes, you have to pull out something, and there's something in there that doesn't even matter. So insulin pens used to administer a patient's insulin at hospitals have a malfunction rate of 9%. This means that out of a box of 200 pens, 18 are defective in some way and must be thrown away. Find the probability of randomly selecting 3 defective insulin pens in a row from a brand new box of 200 pens. If a defective pen is immediately discarded, okay, what is all that? So you go to the end as usual and you figure out what you're looking for, starting with find the probability. Find the probability of randomly selecting 3 defective insulin pens. So you're going to select 1 and the second and the third. And it's not an or, you're not selecting either or, you're selecting 1, then the second, then the third. But it's thrown away, obviously. So you don't even need this 9%. You have to pay attention. So what do we need? If we take those pens and we stick our hand in the pen, the probability that we're going to get a defective pen is going to be what? Now, some of you are going to put 3. That's the wrong answer. You never use the number. You never use the number that you're selecting in your answer. What does that mean? That means that you're not going to have 3 out of any. There were 18 defective pens out of what? So when you stick your hand in there, there's a possibility there are 18 out of 200 that you might pull out 1. That's the first one, time. Now, what's the second one? Have you think about that. You threw away that pen and that pen is gone. Now you go to select another one. How many defective pens do you have? 17, because you already threw 1 away. Out of how many? 200? No, because you threw 1 away. So that's going to be 17 out of 199. Same thing with the third. When you pull out the third pen, that's going to be what? 16 out of what? 198, right? Those are your 3 pens. You chose 1, 2, and then again, I'm going to use decimals all the time because that's what it's going to give me. So the first one was 18 out of 200. The second one was 17 out of 199. And the third one was 16 out of 198. And what's my answer? Now, what the heck is that? What is that E negative 4, 6.22? What is that craziness right there? E negative 4 is scientific notation for your calculator saying that it needs to go, your decimal place needs to go 4 places to the left, okay? So we had 6.21288. I'm just going to write this down on that piece of paper on the side. 6.21288. That's what I'm going to write down. So yeah, and you cannot write this on the test. All right, so I'm just going to write it on the side. 6.21288, something like that, right? 21288. And then it had e to the negative 4. Those of you who remember scientific notation, really good. If you don't, then here's a crash course in it. That negative 4 means we're going to move our decimal places 4 places to the left. 1, 2, 3, 4. So in those places, you have to fill in those little humps. You have to fill in those zeros. So the answer to your problem is 0.00 0.006 because there's a 2 behind it, because you have to have 4 decimal places. And this is one of the ones where you won't be able to keep the fractional one because the fractional number will need to be reduced anyway. So that answer is 0.0006. You don't need to do anything to it. That's a probability. For those of you trying to change it to percent, first of all, you're going to change it wrong. Then separately, it didn't ask you for a percent, it asked you for what? A probability. And remember, a probability is a number what? Between 0 and 1. Let's do another example. Let's try our second example, which is actually different. I'm showing you different examples. Hopefully this helps you learn how to apply the probability rules because they are a little different. Now look at this one. Ashley's internet service is temporarily unavailable. In fact, on any given day, there is a 15% chance that her internet connection will be lost at some point in the day. What is the probability that her internet service is not broken for 5 days in a row? Okay, so how are you expected to know this? I have no idea. We will work it through. What is the probability that her internet service is not broken for 5 days in a row? Now, you do have to recall something. Remember that in the last section, we talked about that sometimes it's either to find the probability that it's broken as opposed to not broken. So we'll talk about that in a second. What is the probability, right, that her internet service is not broken 5 days in a row? So let's think about that. The probability that it is not broken, what does that mean? That's equal to what? That's when we talked to it earlier. 1 minus the probability that it what? Is broken. 1 minus the probability that it is broken. That's the probability of our internet service being not broken. Because we know this percentage here. We know what is the probability that our service is broken. So we know what about her situation? That the probability that it is broken is what? 15%. 15% chance that it's broken. We can't use what? We can't use percentages. So the probability that it is not broken is equal to 1 minus the probability that it is broken. Well, what's the probability that it is broken? We said that it's 15%, but it's a probability, so we need to change it to a decimal, which is 0.15. Are we finished? No, we're not finished. Why aren't we finished? Because this is a probability that is broken 1 day, all right? We're not talking about 1 day. We're talking about how many days. They want to know the probability that it's broken 5 days in a row. How are we going to indicate those 5 days in a row? That's what we need to figure out. How are we going to indicate 5 days in a row that this internet service is broken? So this right here is done over and over again. So this would be 1 day. 1 minus 0.5 is 1 day. But we need how many days? We need 5 days. We need 1 minus 0.15, 5 days. 1 minus 0.15 taken 5 times. So we need to put that into our calculator in parentheses because it's the whole thing. So we got parentheses 1 minus 0.15, close parentheses, caret, that means to the 5th power. If you don't know how to do exponents, check out my video at the end of this video. So that's your answer, 0.4437. That's the probability that her service is not broken. So the probability is not broken is 0.4437. That's the probability that her internet is not broken. 1 minus the probability that it's broken, and they asked for 5 days in a row. If they only asked for 1 day, it would just been 1 minus 0.15. That makes sense. Think about that. If it was 1 day, what's the probability that it's broken? Well, what's the probability that it's not broken for 1 day? 1 minus 0.15, right? Which is 0.85, which makes sense, correct? So you have to do this basically 5 days in a row. That's how you know it's not broken. So either way you want to look at it is fine either way. So let's extend on this prior topic of this dependent probability. So remember, we said the dependent probability, and I'm going to rewrite that. Probability of E and F is the probability of E times the probability of F given that E has already occurred. That's what we did in the insulin pen example. We had the probability of the first one. Then we had the probability of the second one given that you already took one out, given that E, the first one, had already occurred. And then we had a third one given that the other ones had already occurred. So let's see if we can switch back to a little bit of algebra. Oh no. So that formula of their probability of E and F for dependency is the probability of E times the probability of F given that E has already occurred. We can actually mathematically manipulate this to find out this. What if we're looking for the probability of F given that E has already occurred? Remember, we can rearrange this equation. If you remember any algebra, we can divide both sides by probability of E and get a new formula, which is the probability of F given E has already occurred is equal to the probability of E and F all over the probability of E. This formula right here is called conditional probability. That formula is called conditional probability. Just a rearrangement of the formula when we're talking about dependent events. When we rearrange that formula, we talk about conditional events. We can get the probability of F given that E has already occurred. Let's do an example. A high school swim team consists of 3 seniors, 2 juniors, 4 sophomores, and 2 freshmen. A relay team of 4 swimmers is chosen at random from the team members. What is the probability that the last swimmer chosen is a sophomore, given that there is a senior, a junior, and a freshman already chosen? Well, if there's a senior chosen already, that leaves 2 seniors. There's a junior chosen already, that leaves 1 junior, and then there was a freshman chosen already, that leaves 1 freshman. So the total amount that we have, all those other people are gone. So for our 4th choice, remember we have 4 swimmers, we're on our 4th choice. 1, 2, and 3 is already happened. So on our 4th choice, first of all, remember probability is out of a total. What is our total? How many swimmers do we have left? Well, we have 2 seniors, 1 junior, 4 sophomores, 1 freshman, 4, 5, 6, 7, 8. So we have a total of 8 swimmers left. Then we're looking for the probability that the last swimmer is a sophomore. How many sophomores do we have left? 4. So 4 out of 8 is going to be the probability that you choose the last one as a sophomore. Remember, one answer or the other. Let's move on to the next example that talks about conditional probability. Now, that may be controversial because different students will approach this differently. This is the method that I teach to approach this problem. There is another method that some students find easier. However, this is the most direct method for most students who struggle on this concept. You will look up other YouTube videos and you will find an easier way for some students. For most students, it's just more confused. So if I take a look at this, I got this chart of Mrs. Harry's algebra class. She has 42 students in total, and they're all classified by academic year and whether they're in-class instruction or online instruction. She randomly chooses one student's homework to grade first. So the question A is, what is the probability that, and look at what I'm writing, that she selects an in-class student, I'm gonna call it ICS, with the line, given that will always say given that she chooses from only sophomore. Now let me write the probability formula that we just went over here. The probability of F, given that something has already occurred. Remember, if we scroll back, we have worked that out. That is the probability of E and F divided by the probability of E. So let's just put that down. That's equal to the probability of E and F divided by the probability of E. Now this goes back to what I told you before about writing out the words first and then putting the numbers in. Why? Because it just keeps down the confusion. So if I rewrite this like the formula, so I'm going to go with the probability of what? E and F, which means that he's a sophomore and on in-class instruction student all over the probability of E. What's E? This is F, this is E. The first one is not E, it's the second one. That's what you have to remember about this formula. So you can put the letters on top however you want to do it. So that's going to be the probability of what? Of sophomore. Now all I need to do is put in the probabilities using the chart. This is the way I do it. There is a more common way to do it, but I like this way so I don't have to think. So now I need to look for the probability of a sophomore and in-class instruction. I look up here, I look for sophomore and in-class instruction. I'm not going to put 4 there because this is the probability of that. So I have to put what? 4 out of the total of 42 divided by, now I need the probability of being a sophomore. Well, the probability of being a sophomore is here. So the probability of being a sophomore is 9 out of 42. If I pop that in my handy dandy calculator, 4 over 42 divided by 9 over 42. Need my parentheses. Now I'm going to show you the decimal answer, but I'm going to show you also the fraction answer. It's actually 4 out of 9. So some students are 0.444. So some students will say, I could have gotten that by just looking at the, good for you, okay, good for you. And I hope that all works out for you. May the odds ever be in your favor. But if you do it this way, you'll get it correct. Either 4 out of 9 or was that 0.4444. Some students say, I could have chose that was going to be 4 out of a total of 9 because these are my sophomore students. Do it that way if you want to, right? I'm just showing you the way that keeps you on track and keeps you balanced. Let's do B. I'm going to do B the same way. What is the probability that she selects a junior given that she chooses an online student? So that's going to be the probability that they are online and a junior divided by the probability that they're what? The second one divided by the probability that they're online. And now I can just go and be merry. What's the online and junior? So online junior is 2. 2 out of 42. Remember, that's a fraction. You can't just write 2 and then put it over the bottom and call it a fraction. 2 out of 42. All over the probability of being online. Online is this column here. That's 13, 18, 20, 23. 23. So 23 out of what? Out of 42 is going to be your answer. And when you put it in your calculator, you'll get 2 out of 23, which is going to be the same thing as 0.087. And I'm going to show you this one, 2 out of 24 out of. The reason I wanted to show you this one is because you see that what happens with the rounding, with the decimal, you get 0.0, you get 0.08695. Well, when you take that 5 and you round the 9 up, you also got to take that 9, since it's a 10, and round the 6 up to a 7. That's how we get 0.0870. Hopefully you remember those rounding rules. I just went over them real quick. 0.0870 because you need 4 decimal places. Lastly, they want to know the probability that she selects an online student given that she chooses a junior. Again, I'm going to do my same rounding, the probability that she's a junior and an online student, all over the probability that she's a what? A junior. All right. So a junior and an online student. Junior and an online student is 2 out of 42. See if I can squeeze it down here. All over the probability of being a junior, which is 6 out of 42. See that right here? That's all the juniors straight across. 6 out of 42. So that probability is 2/6, or that's equal to 1/3. Or you can write what? 0.33333 for your answer. And that's conditional probability. I'm telling you to use the formula. If you use the formula like I do, you never go wrong. But if you start trying to think of how to read the chart, you're going to get confused and not know how to read the chart. You know I need a mantra right now, so I'm going to go get one.
Walk slowly and talk slowly. You are.
This is long. So this is the last concept in this section. Just hold on. So the next part we're going to cover is called the fundamental counting principle. It's about multiplication. So let's say, remember we learned if you multiply the probabilities together, all right, we go from only being able to do one trial to doing multiple trials. So where we could only pull out one card or pull one marble out or flip the coin and do one head, that's what a single trial. But when we got to multiplication, we learned that we could do multiple trials. So once we got to the multiple trials, we said, okay, now we can do that. But on top of that, we also know from back when we were learning how important it is to do what? To count our outcome. In order to count our outcome in multiplication, we have to do something else. So we have to count our outcomes. Remember, in addition, we counted our outcomes by making a tree diagram. In multiplication, the tree diagrams would be impossible and take too long. So we have the fundamental counting principle. So the fundamental counting principle is for that multi-stage experiment with so many stages, so many outcomes, second stage, second outcomes, and we get all the totals together. So it's just going to be the probability of your first outcome times the probability of whatever your second set of outcomes are. An example is better than trying to explain the principle to you with all these words. Let's do this problem. Now I'm going to rearrange this problem for a second part, but just to show you the difference between the fundamental counting principle. So this problem says determine the number of 5-digit zip codes that can be made from the digits 0 through 9. Assume that digits may be repeated. Assume that digits may be repeated, which is important. So if I go with the problem the way it is, they may be repeated. You have 5 digits. You have 1, 2, 3, 4, 5. So 0 through 9, if you don't know, is 10 digits. So your first digit can have 10 digits, right? It can be anything 0 through 9. So the second choice you have is 10 digits. The third you have is 10 digits. The fourth you have is 10 digits. And the fifth you have is 10 digits. When you multiply all those together, because remember, when you're going this one and this one and this one and this one, it's not or, because you need them all. When you multiply those all together, you're gonna get 100,000. But let's say that you could not repeat a digit. So not repeat a digit. You still have the first one, the second one, the third one, the fourth one, and the fifth one, right? But this time you can't repeat it. So if you take a letter, you take the first one and you take a number from there, that number is no longer accessible for the second choice. And those two numbers are no longer accessible for the third choice. And then those three numbers not for the fourth choice and not for the fifth choice. So as you do that, that's a little bit different. So that's 10, 9, 8, 7, 6. Multiply that together and we get 30,240. 30,240. Look at the difference. We'll talk about this in the next section when we talk about permutations and combinations. Look at how low this is when you don't repeat, when the order matters. Look at this. This is 100,000. This is 30,240. A big difference between the combinations you can have. Again, that's coming up in the next lecture. So let's do this second example and hopefully call it a day. This is a long video, a lot of information. Don't forget to comment, like, and definitely subscribe. I did a lot of work for this one. All right, so this is our last one. There are 6 children, 3 first graders and 3 second graders singing in the school program. As they line up to perform, the choir director insists that the first person be a first grader and the last person be a second grader. Now, how many ways can the children line up? Now, this is interesting because some people try to go in order. We won't try and go in order. We'll listen to what's going on. So we have 6 children. 1, they all are in it. So it's multiplication. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, right? So the first person has to be a first grader, and there are 3 first graders. There are 3 first graders. So you get to pick one of those first graders to be the first person. Now, I don't care how you do it. I'm going to do the last person. Now, you can put it at the end, or you can go next to it. Doesn't matter. But the last kid has to be a second grader. So you have to pull that out. So that's going to be out of 3. So it doesn't matter. The next kid, if you want to call him, and you can throw this kid to the back, but the next kid that's going to come up, how many have we used? We've already gotten rid of 2. So the next number of kids we got our first kid and our last kid. So that's 6 minus 2. So we have 4 kids left. Everybody cool? Then after that, we have 3 kids to choose from. Doesn't matter what grade they're in. He didn't care what order those were in. And then we have 2 kids, and then we have the last kid. So it would be more complicated if you try to think of it differently, and you're going to get 216 possible ways that these kids could line up. So that was a lot of information that we just covered here. A lot of information in that one section. I suggest that you go and you do more examples, but hopefully I've given you enough examples to get you started and that you understand. If you have any questions or concerns, please comment down below, and you'll see the videos up here if you need to figure out how to do things in your calculator, or you need to figure out from the last section going back over the section 4.2 addition. Thank you, and this is Professor Sampson from PS I Love Math, and I'm out.